Okay, so before you start, let me tell you something about the Marcus reaction. So, what we have come across in the reaction mechanism is that whether it is dissociative mechanism or associative mechanism, so if it is ligand substitution reaction, and as you know, in nature, the electron transfer is extremely important in the nature, I mean, the reaction mechanism. So, and there were some block, and people couldn't understand. So, what is your? I mean, take it as a story. I mean, some of this portion will be there in the course, but some of the things will not be there. But I just want to give you a little perspective about the electron transfer reaction, and in detail you will learn it in the fourth year. So the point is that uh, our general idea is that if del zero is negative, then you have a reaction that is thermodynamically feasible. And there might be some steric hindrance, there might be some other problems in the reaction that might disturb you or that might not give you the product. But if you cannot find out the reason for non happening of the reaction, and you can see that the thermodynamics of the reaction is I mean, thermodynamically the reaction is feasible, so that becomes a little bit worrying. And it took for the electron transfer reaction, when people could understand the reaction mechanism, that this it is going to outer sphere, or it is this is the way it is Marcus equation is evolved. And then it took almost 30 years to understand that why a thermodynamically feasible reaction is not happening. So what could be the reason? So let me tell you the story, and then I shall show you the graphs. The first thing is that, as we discussed in the last class, that you need some degree of reorganization. Just a minute. Let me close that door. So, this what we have understood from the last class is that we need some reorganization. So, what happens? You have two molecules. These two molecules, there will be an electron exchange. Now, this electron exchange is only possible when they uh, reorganize themselves to such a state that that immediate electron transfer take place. So there are I mean, if you go through the Marcus equation and Marcus relations, all these things, there are too much of quantum mechanics and these, I mean, along with thermodynamics, there are too much of quantum mechanics is also involved. But we shall not go deep into this quantum mechanical aspects or all these things. We'll try to understand it like we can see that physically. So the first point is that it is the Frank Gordon principle that when the electron transfer is taking place, when it is in such a so when the electron transfer takes place, then there will not be any a nuclear organizational change. So if this is the point, like so as you can understand, so one electron when transformed from one of the molecule metal to another metal, there will definitely be some changes in the bond length of this. Let's say there are one metal chloride bond. So metal is, if the metal is 2 plus and if the metal is 3 plus, so definitely this bond, I mean the existing bonds, because as you can understand, in case of only electron transfer reaction, there is no bond breaking or some such things happen. So what is this? Only the electron transfer. So if it is single electron transfer, or it can be two electron transfer by molecule the electron transfer, that can happen. So if there is no such bond breaking, but still there will be some bond changing the bond length or all these things, and then the as you can understand that from changing from 2 plus to 3 plus for a species, and the changing from 3 plus to 2 plus for the another species, there are changes in the overall charge. So when the overall charge, the compound is also solvated, and this solvation actually helps it to reorganize. So it is said that this so they need to reorganize in such state that when the electron transfer take place, at this moment there is no change in all these things, and after that they will take the changes among themselves. But during the electron transfer there will not be any such changes. Now if this is the reorganization energy, then what are the other parameters do you have in the reaction? So you have del G of this overall reaction. What is the del G of reaction? And that must be negative. So that we all know that del G of a reaction must be this negative to have a thermodynamically feasible reaction. So, and there now I shall go to the parabolas to make you understand that with this del G, this thermodynamic, del G reaction, there is another is the del G of the reaction transition state. So what is the transition state? So as you can understand, for every reaction, every species, there is a lowest energy term. It may be the reactant, it may be the product. So there is, if you just draw it like parabola, and you can know how to draw it, this parabola, and this Morse potential, in this way we draw, and there are vibrational layers in that, and then if you have the lowest energy, so that at the lowest tip of the parabola, we say this is the stable state. So it is not definitely not that for both the reactant and product that they this reorganization the point at where they are reorganizing is the same as that of their lowest energy in the curve. So there is another point, and the difference between the reactant lowest potential and that of the transition state. So we have the del G of the transition. Now, before I go to the point, there are a very I mean physical meaning of this uh, Marcus equation is that lambda is called the reorganization energy. Now, what could be the reorganization? Let's say, I mean, if you just look at the society, or if you look at the nature, you can see that if someone has to, or something has to reorganize, then it depends on the particular person or particular situation, that how long will it take to reorganize, right? So some, I mean, if we look at this human being, so for some work, you need some mental preparation. So some people take very quick decision to take the mental preparation for such one fixed work, and some other people will take a long time for that particular to take that decision, and some people will take the midway of these two. And this decision as you can understand, depends on too many things, like if someone needs something, so if some support is there, if that work needs some support, so if some support is there, that they can take very quick decision, that you have the support, so I can do that. If someone do not have the support, then they will try, I mean, as we are telling that the reaction is thermodynamically feasible, so everyone is trying to reach that point. So if someone do not have the support and all these things, and then they will take much time, but they may end up with this reaction. Now what happens, that I am coming to the slides, and let me tell you one thing. So here I kept one slide for this marker, so you just read it. It's nice to read all these informations. And then what are the theories mostly found, this theory is extremely important in electron transfer between any reaction. And if you just go to the Nobel Prize yesterday, then you will see that there are too much of this reaction organocatalysis. And if you just see David Macmillan's papers, and you will see that in all the cases there are one term, that is SET. And this SET means single electron transfer, and you will find in all the cases this Marcus equation is one of the important problem, because now you can sort out the problem with this Marcus equation. So very easily, you are, all of you are familiar with these things, like what we draw. So we all are I mean we are We all are familiar with this, writing this reaction rate like this, where this is the reactant and this is the transition state and this is the product and this is the del zero of the reaction. So, I mean, all of you. So, how does this come? So, if you take the reaction, this is reactant and this is the tip, and then you have the product. Now, when we look at the Marcus equation, then this point is very, very important, and it is said that this point is actually the electron transfer take place. And if you go to any in extension, when you will read, you will see that here also you can write one thing like this, covering this one. I mean, in that way it is written. And also these are the position where this is closely, this reorganization has take place, and here the electron transfer actually occurs, and this is the called this del G. I mean, from here to here we call the del G of transition, right? Now in the next one, the same thing, this Morse potential, and then you have the vibration energy. It is just to give you once again the idea of these things. Now what happens? Okay, let me show you. So this parabola, see, drawing of the parabola is very, very important. Now what could happen that you have self-exchange reaction. Last day also I told you self-exchange reaction, and if I draw it that way, I might not be very can draw this parabola very right. So in that case, okay, one thing is very important. When we are writing this reaction coordinate for this, I mean, explaining this electron exchange, we are considering the reactants as well as the solvation also. So taking care of all these things, we are drawing this reaction kinetics. So from here, one thing is clear, that this del G zero of this reaction is 0, because for both of them it is the same. So if this del G zero is 0, and it will come as that the I shall come to this, and lambda, this amount is the lambda by 4. Here I can show you, and this del G internal, so that one del G internal becomes lambda by 4. Now the point is that this reorganization energy, and you can ask that what that reorganization energy actually means. So this reorganization energy is the, I mean, here you need to go to the quantum mechanics a little bit, and I am not showing you, I am just telling you what is the point. So here actually this is, if we just extend, and from this point, if we draw this value, I mean, I cannot write. So if this is, then it becomes like this point, this is the reorganization energy, and it can be calculated. I mean, it can be calculated in that way. I mean, here it is lambda by 4. Always it happens that if del G 0 is equal to 0, then del G internal, this internal, or del G, actually, what initially it was the term that this transition state, but what they are I mean, when this Marcus equation comes, they are not ready to tell it a transition state because it is the barrier that they have to cross. So they kept it as del J intrinsic barrier, so INT. And then this is the lambda by 4. And as you have understood that reorganization means energy reorganize the nuclei without electron transfer occurring. Next, so what are the probabilities? So if you take a del G internal intrinsic, then it has been shown that, so we are coming to the outer sphere reaction. So we are interested in only outer sphere reaction, and all other reaction we shall just tell you the story. That's it. So if we take this intrinsic barrier, so del G intrinsic becomes the, if you take these two reaction, so these two reaction has two state. I mean, if you take OX1 plus RAD1 equal to RAD2, RAD1 plus OX2, right? So if you take one pair like D going to D plus and A going to A minus, so if you just take the self-exchange, I mean, when you have only self-exchange reaction, then you can draw it in that way. But when these D and A are, so there could be two, so D and A is same, then we can draw the picture like that. But if D and A are not same, this picture is not, this picture you cannot say, because then these two potential will not be the same. One of them will be up and one of them will be down. One of the, and if the, so it could be like this, exothermic reaction, or it could be like that, but this is much more feasible because here you have the del G is negative, del G is this, right? This, right? But here in the discussion, let me show you that if you have D and A are the different, then you have del G of del G intrinsic for the donor and del G intrinsic of the acceptor, and you can have this del G total intrinsic is del G donor plus acceptor divided by 2. Now, if you have this kinetic barrier del G, and if you have two of them are different, then we can define this is the del G intrinsic, as I have shown you in the last day also, that if del G is this is not self-exchange, and if you put the self-exchange here, the things become same because del G becomes 0. And lambda square by 4 lambda, and it is 1 by 4 lambda, as you can understand that del G is equal to 0 for self-exchange and del G internal. From this reaction only, it has come that 1 by 4 lambda. Now, sorry, 1 by 4 lambda. Okay. Now, if we go to the reaction rate, so now you consider this particular thing. So this is the K of electron transfer. Now this K of electron transfer is this kappa, as I told you, kappa is the probability of this, how many times they are facing, and then nu is that how many times they are facing, and then how many times they are electron transfer is taking place. This is completely, this is Boltzmann constant and Planck constant and the temperature. So these things you know it comes, and then reorganization energy del G 0, and again this R and this T. Now here I just kept these things for your this understanding. Now a little bit of idea about that, how does this reorganization energy depending on the orbital. Like if you transferred an electron from a non-bonding orbital, you just think of it. you have a metal bonding orbital, you have a metal non-bonding orbital, and you have a metal complex, you have a anti-bonding electron. Now, when you have learned to uh, calculate the bond length of a reaction, have you ever been involved the non-bonding electron? No. Number of electrons in bonding orbital minus number of electron in anti-bonding orbital. So I think all of you are have done this. So if you take an electron from bonding orbital, or if you take an electron from anti-bonding orbital, that has much effect on the bond length of the any one of the bond, right? And that actually is the point that you have to reorganize, so that during the electron transfer that is not much affected. But if you take an electron for non-bonding orbital, you can understand the reorganization is quite easy, because it is not affecting the bond length. And also, how does this reorganization take place actually? So if there is M plus, so these M, all these things, the solvent molecules in some cases um, organizes it so that the solvent is so important for reorganization, that whatever effect is on this particular molecule after electron transfer, for let's say for donor. So donor is coming to a point and there are too many support from the solvent, so immediately the donor gives the electron, and immediately whatever shock that has been suffered uh, by the molecule is supported by the solvent. Like someone is there standing and something punches it, but if there are too much of support from this side, that this position remain the same. So in Frank-Cotton principle, this position has to remain the same. So if there are too many supports, like solvents are supporting this particular molecule, the D, and then also in case of A also, this is reorganized in such a state that if electron comes, the immediate effect of this taking up the electron is supported by the solvent. So if there are no solvent in the vicinity, then it becomes difficult to reorganize or take the difference, and then sterically it becomes difficult. If there, when can solvent molecule cannot approach? When the molecule is sterically, steric hindrance is there. And also, I do not know whether I have written or not, I am telling you, steric hindrance number 2 is the protein molecule or enzyme kinetics, where you have the protein pockets. This is covered by a lipid molecules and these other things, so that the solvent molecules cannot uh, enter these groups. But the point is that there are some other things to support, and for that reason they have specific pockets where the reaction take place. And you have learned very well in the biology that if you just denature the protein, or if you take these things in any of the position, the reaction will not take place. So all these things are very much related with the reorganization energy. So if simple meta-valence, you can say it is well in excess of 1 eV, and buried in redox centers, it is as low as it could be 0.25. So this happens. Now the point is that this I told you. Now let me tell you this part you should know, and at least this part you should learn from here, that if you take a simple outer sphere reaction, simple outer sphere reaction means, let's say cobalt ammonia plus chromium, let's say cobalt L1 6 plus chromium L2 6, like this, plus 3 plus 2 2, cobalt plus 2 2, chromium plus 3. So this simple reaction if we take, and here we can use the solvents, then you can have this reaction where this K1, K2 is equal to K1, K2 is the rate constant for the reaction is K11, K22, and then K from the log equilibrium constant from the thermodynamic parameter, and F12 is there. And what is F12? I'm coming, and this is called Marcus cross relation. And here you have this for F12, and this term is the consideration of this non-linearity of this function, and that can be okay. Now, when you have del G0 is not very high, why it is problematic, that I shall discuss. And very high, then you can have this F12 can be set to 1, right? And when you have, and how the reactions are highly favorable thermodynamically, then this LFER breaks, and that is the problem with the Marcus, that I shall come. But at this point, then you have to calculate this in that way, where Z is the I mean, you can, here I have given one theoretical approach, but in very easy way, you can this the number of collisions. This is the best way to understand it easily. The number of collisions. So when it is this del G is very negative, then you can take that reaction, this log F2. But if you have all these parameters along with the Z, and then you can calculate this constant of proportionality from there. I can give you one example. Okay. Now I shall give you three situation, and these three situation, there is no white page. Okay, there are three situations where you have del G is 0 is negative. Normal reaction is not too negative, and del G0 is it can be a little higher than that lambda, or it is related to lambda. It can be a mod of del G0 can be a little greater than lambda, or a little less than also. It is quite normal, but negative, and it is not too negative. Here I am writing this because this is important. It's not too negative, right? And then you have a rate of the reaction, a non-moderate rate of, you will have the reaction is going. So rate of the reaction is measurable. Or modest. Modest I am not want to write because that we have to compare with something else. Now you have a situation. So here you can see that this is del G, this is the situation. So you have a del G0 value, and from that you can see that lambda is a little more than del G0, but it is not too high. I mean, this parameter is not that too high for this. Now, okay. Okay, now here you come. So from here it will be a little difficult, but I'm telling you this idea that if you have del G 0 is negative as I told you, and you have del G transition is greater than 0. So you take the first step. So the look at the parabola. This parabola is like that. Parabola is like that. Maybe from all the parabola you will not understand, but still let me try. So this is the point for del G intrinsic. This is the point for del G 0. So del G 0 is negative and del G intrinsic, and you have a rate Ka. Right. Now you take this point. Now here you can see that at this point you do not have any del G intrinsic value. So del G intrinsic is 0. So if you do not have overall reaction, del G is negative. Del G is negative, and here the del G value is equal to minus of lambda. It comes with the calculation. So del G value is equal to minus lambda. So you have, so how does it come? If you take this reaction and if you just take that del G internal is equal to 0, then what comes? Lambda plus lambda G squared equal to 4 lambda. And if you do the reaction, do the root and reaction, it will come. I mean, you have to consider some points that it is negative. You just do the calculation, it will come almost, the value will come almost as del G is equal to minus lambda. And this is called the barrier-less reaction. Barrier-less reaction. And next, the problem comes what Marcus is much more, Marcus is very famous for. Now, as del G0 approaches minus lambda, the reaction rate increases. Means that whatever reaction rate is there is more than this. So Kb is greater than Ka. Right? Is this understandable? Let me know. Then I shall go to the next one. Is it okay? When any one of you are there in the class, so please let me know. Is it okay whatever I told till now? Now this actual thing comes that if now del G0 is such that it even become more negative. So in become more negative, so what we are telling that del G0 is, so del G0 is less than minus lambda. What does it mean? That del G0 value, if you take mod, then mod of del G0 is much greater than lambda. And in that case, it is very difficult that for the reaction, and how people have tried, this is the point where del G is minus lambda. And what happens now, if you look at this, that this is the del G0, so it is increasing. So initially, and this is the KET. So what is happening initially up to barrierless point, it will just increase. And after at this barrierless point, this is the, so here it is the A point, this is the B point, and here comes anywhere, it is the C point. So what is happening after that, reaction rate decreases. Now, okay, fine, reaction rate, if it is decreases, we can understand that reaction rate decreases, we don't have problem. We can know that reaction rate is decreasing. But the point is that you cannot have electron transfer. What you can see that after this, sometime after this, maybe when it is increasing, so if del G0 is increasing, become more positive, and after some point, more negative. And the point is that what actually amazed people. So this is the, let us tell that del G becomes negative. So reaction if is del G0 becomes more negative, and at some point, after some point, no electron transfer. This is the no electron transfer at all. And this is the problematic, that the thermodynamics says that the electron transfer is taking place and there is no electron transfer. So what is the reason? So this is the Marcus, actually it took 30 years. So what is happening, as you can draw, calculate with the del G, lambda, all these things, that del G becomes more negative, then the reaction rate initially is increasing, then it becomes barrierless at point, and then it is decreasing. But the point is that in this graph, at some point of time, with the solvent and all these things, it is taking for the reorganization, you have the solvents, you have the system, and the system is not reaching at all at these points, and it is the diffusion that is taking part of the leader, and the electron transfer is not at all taking place, right? And also the reaction rate is much slower, and even if it is taking place, it is much slower in that case, and is very to escape this leveling effect. So what people now could do, these diffusions, this tunneling of this energy, and that cannot be avoided. And what people have done, that if the system is like that, then with the change in the ligand and change in the solvent, change ligand, change solvent, people have tried, and then they could manage to keep the highest, minus, where the point is that del T0 is equal to minus lambda. This point they could manage to keep below this K diffusion point, and then it is possible to understand that that this del G0, the reaction is now feasible, and you can see that what is happening. And this is again another point to escape diffusion leveling. So del G0 then must be much greater than reorganization to escape diffusion leveling. And there are some reactions that actually they have done with this type of reaction, that where they can manage the leveling effect. So this is the story, and let me know if you want to know anything from here. Then we will go to the this problems with the this rate of reaction and the reaction kinetics. So let me know whether it was understandable. I mean, I have not went to very detail of these things or like this. And next we'll go for the problem. So let me show you that how to approach the problem. What does these problems says, and then what does it mean? How to read it? It could take time. You can tell me. Yes, I can tell you the book mainly Stewart Atkins. So whatever I told you, that's inverted region, that I took only from the journal paper, and you may not need to read all these things, right? I mean, if you want, I can send you the detailed presentation also. And also in the presentation, you will see there are some journals, and I took from these journal papers to understand the things. And then, I mean, we have read it in the higher classes, and then if whatever you needed is there in the Stewart Atkins books. Right? Stewart Atkins, and if you have Douglas McDaniel, there also you can find something. So the part that you need to read is only that what is Marcus, this parabolas, how does it look like, and then you can just look at this, how can you put it in the uh, outer sphere reaction. And if someone has more interest, any time you can tell me that you need to understand these things. So shall I start the question answer? So how to read the question, where to give the emphasis. I have kept some questions only from Mislattar, and you can go through this Mislattar, Atkins, and I shall also give you some more problems. One assignment I shall give, and without that assignment also I shall give you some questions to read and to attempt. And if I know that all of you will not do attempt this, but if some of you together in group can try to uh, look at the problem and solve the problem, and if you feel any problem, you can let me know. This is just for practice problems, right? Because once you look at the 5 books, there will be 5 chapters, and there will be too many questions. And these questions, sometimes it is beyond your understanding, because it is in the research level, some questions are there. So I shall try to pick up some questions for you to understand the things better. So I'm coming back within 2 minutes. So can you unmute your this and ask me the uh, interact with me, or you need to follow the chat box? Please check. If you can unmute, then we can just go to this presentation and can discuss. Okay, so can you unmute Vidul? You just check.
Yes, ma'am.
Okay. So then let me go to the question. So the question says that this carbon monoxide exchange from this chromium cobalt 6, chromium carbon monoxide 6, 13CO, and this rate depends on chromium carbonyl whole 6, but independent of the concentration of 13CO. So what does this indicate? The first reaction, what does this indicate? It's very easy. Any one of you, please. So what is the mechanism could be? So I'm giving you the choice, dissociative, associative, what is the reaction pathway? For the A reaction? Please, this is very easy. This is very easy. Please let me know. Yeah, why people are writing? You cannot unmute? Kundan? Yes, dissociative. Don't write maybe. Yes, it is dissociative. It's very simple. So from this, it is dissociative. So if it is possible, you just tell me. Okay, so this dissociative. Now the point is that if the question asks you to write, I mean it depends on the question, and if the question tells you to write how to write, then you just write this. This is the reaction CrCO5 plus CO, and this is the, and then CrCO5 plus 13CO, and CrCO whole 5 and 13CO, and this is the slow reaction. So this is the rate determining. So write in that way. So the next one. So next one, what it could be? I mean, why does this rate law have two terms? So this is the practical thing. The rate law have two terms. So what are the terms says? Two terms. One is, so can you see the this presentation till now? Still now, can you see the presentation?
Yes, ma'am.
Okay, so I mean it is smaller, right? So you just tell me that what is the what why it could be, it contain two parameters. Why it contain two parameters? So what could be it? It is the I mean replacement, right? So if we look at this reaction, it is the replacement. This carbonyl 6 was there, and now you have carbonyl 5 and PR3. So this is substitution, ligand substitution reaction. Now this ligand substitution reaction, the first one you have given this dissociative mechanism. So now if it two, now what is this complex? CrCO6. Look at this very well. Here you see that CrCO6 and PR3. So what is this? This is the, what is this? CO6 is there and PR3 is there. So and your end product is CrCO5 PR3. So what does it call? Quick. Associative. So actually what does it mean? That the reaction when you have PR3, then reaction could proceed through dissociative as well as associative. And it depends on the addition of these two. Is it clear? So you have learned that there could be dissociative mechanism, there could be associative mechanism, but it is not your, you cannot dictate that you go through this dissociative or associative. So if there is possibility, they can use both the mechanism and the in whatever way it gives more. K1 may be greater than K2 and K2 may be greater than K1. Now the next question takes care of that. For the general reaction in part B, with bulkier ligands tend to favor the first order or second order pathway. So this is the second order because it has two parameters, right? So which one is, if it is bulkier, so what will happen? So if PR3 is bulkier, then what? Then first. So it's very easy. I just want to show you. The second question. So this what you have to think. You have to think in terms of bonding parameters. So account for the observation that two separate water exchange rates are found for C copper water H2O6 2+. So think in the, I'm giving you the hint, think in the concept of bonding. So why copper is special and what is the, always you look for copper 2+. That will give you the answer. Copper H2O6. Look at the copper and then think of the what are the bond that copper, even if all the ligands are same, so what could be the difference? Yes, Jahn-Teller distortion. Fine. So Jahn-Teller distortion, what Jahn-Teller distortion is making difference over here? What Jahn-Teller distortion making, how does it affect this particular reaction? Two ligand exchange. So if there are two water exchange, so what does it mean?
Axial bonds are weak and equatorial bonds are.
So axial bonds and equatorial bonds. So that is the answer. That axial bonds and equatorial bonds are different, and for that reason, two different ligand exchange. It's very, in that way, you have to find it out. Okay, next is the question. Okay, here, can you read the question? Can you see this question? So let us understand the question. The rates of exchange of CO on C-square planar IR3 complex have been observed for the following reaction 298. So these are the reaction rate, Cl, Br and I, right? All three reactions have large negative values of entropy of activation. So here, once you see it, you just see what you have to think of it. It is square planar. Square planar ligand exchange. Right? Large negative values of entropy of activation. So the entropy of activation is large negative. What does it mean? That system become stabilized in the
associative.
Okay, associative. So associative. Now the second point is very easy. It is written the strongest trans effect. So why the reaction rate is different? Because all of them are associative, right? And it is the only the same thing is adding to the system. One CO is going, another CO is coming. So why this difference? The difference is due to trans effect. So why? And then you tell me that on this basis of data, you do not have. Let's say you have forgot the trans effect series. Then from there, which one is the easier and which one is the difficult? Look at the metal. If it is iridium, it is in the 5D. Then which bond? Put the X, and which bond is, easier, stable. And from that data, you tell me. The data is with you. What is the answer? I have written in the chat box. Associative factor. Size. Okay, then. Which factor is considered? Which factor? Size factor is considered, yes. Then size factor is considered, then what is the which halide exert the strongest trans effect? So you just see that I and IR goes well, and that K you just see that 98. So it's quite way high. I mean, if you have I minus as X, and then the reaction rate is extremely high, right? So I is imparting, and for that particular reaction, iridium and I, for this particular reaction, I has the strongest trans effect, right? Okay, so the next question. This question you may not remember or may not coordinate it well. So, I mean, I think you have not got the time for this, and I have also went very quickly through this. But let you try, and then I shall tell you. So, is the reaction cobalt NH3 whole 6 and chromium H2 whole 6 2 plus likely proceed by inner sphere or outer sphere? So, if you look at the, yes, Kundan, right. So this inner sphere or outer sphere. So if you think in the way that inner sphere, what does you need? And for outer sphere, outer sphere, it can happen anyway. But first you look at the inner sphere, and then if consider the factors that could help it to go through the inner sphere reaction, and if that factors fails, then you go to the outer sphere. So what are the factors that, if you remember, or if you could correlate? During this, the question, I could understand that maybe I have not told you that part clearly. So what are the factors for this inner sphere reaction? What do you need? Quickly remember that there is a precursor complex, then there is a bridge, and through the bridge, the reaction, the electron transfer take place. Any idea? Everyone is silent. So first thing is that you see that there is no a product has been given, right? So no product has been given that what would be the ultimate reaction. Here the factors you have to take that only that ammonia, yes, there could be, there is not that much interesting bridging ligand is there, right? So what can join the both the things? So one of the factor is that, and the thing you need to read is the lability of the system. If you write it uh, properly, you will see, read it properly, you will see that the cobalt 3 plus is not at all a labile system. So for inner sphere reaction, the factors, one of the factors is the bridging ligand, the bridging one, and the another factor is the lability of the metal center. So the lability of the metal center. So here this metal center is not at all labile. So even if NH3 can act as a bridge, then it will be very difficult for this cobalt center to lose that NH3 to chromium. And that actually stops this reaction and this becomes outer sphere mechanism. And now, if it has to go through the reaction mechanism, I mean, that NH3 will build up. In that case, it may go to through the ligand exchange reaction with the ligand substitution reaction. Is it clear or need more clarification? So let me go to the next. If you have any question, you can ask. Okay. Now this is one of the reaction. The rate constant for this exchange reaction so what is the reaction? Everyone is silent. So please read the question and let me know what is the reaction. What happened? So look at the ligands very well. Look at the ligands. Can you read the question? Read the question first. Self-exchange reaction. Fine. Self-exchange reaction. Then what is the X is an uh, F minus Cl minus Br minus this one. So if X, so here it is chromium 4, it is chromium 2, and then here it is chromium 4 and chromium 2. So this is bimolecular, inner sphere reaction which involves two electrons. So I am telling you it is inner sphere reaction. So now you tell me that why this is the value. So these are all of them are bridging ligand, as you can see. So this will go to the inner sphere mechanism. And if this goes to the inner sphere mechanism, then please explain the rate of the reaction from here. Why the rate is such that? Why the reaction rate? I mean, for bromine it is very high, and let's say for NCS it's the lowest, right? The rate the reaction. So what is the reason? Yes, size factor and electronegativity. So from there, from some more question papers, you can understand that these factors actually controls this reaction. And in most of the cases, when you will have these questions, you can see that the questions, the result is given, and you have to find out the reason for that, right? So here, the first, once you have the bridging ligand value in the question, and the rate depends on this Br minus Cl, all these things, immediately you have to understand that there is a role of the bridging ligand. And as the reaction, all other, I mean, chromium X2 or 2 plus doesn't exist. There are some H2O whole 4 and all these things are there, definitely. And here, as all the other things are not have not given, only the X is there. So also you don't need to think in the way of this trans effect. So immediately, if the electron transfer takes place and this self exchange, you have to go for the either. So it is redox reaction, and then you have to go to the inner sphere or outer sphere. And as the rate depends on the size, the ligand, the X, it means that it is the inner sphere reaction. So, do you want? I can give you another thing that you have for this outer sphere. So let me just draw, and then if you want, I can give you two or three more. So if you have a reaction, let's say ball by p whole 3 plus so this reaction, as I told you, that is so this parameter we will take, and we can write a power of K1, 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 K1. And what it is given that K11 is the reaction of these ones, this self-exchange. So K11 is, it comes in the, this type of reaction comes in all 3 plus NAT and GRE, everywhere it comes. Right, so this is the self-exchange, and K11 is 9. At 0 degrees centigrade, and equally you can write for this tarpidine one, and then K12 is equal to 48 m plus S inverse at 0 degrees centigrade, and then reduction potential generally is given, and from reduction potential you have to find out the K from this reaction. Del G is equal to minus ln K is equal to minus NH is 0. Right. So reduction potential is given, and from there you can calculate reduction potential is 0.31 V and 0.34 V for evolved by P system and evolved RP system. And from there you can find out the value of log K12 will come at 0.553. You can do the calculation. And K12 is equal to 3.57. And then K12 will fit in the formula, and it may come at 39. So generally it will be given more marks, but it comes. Or I am just giving you one of the formula. I mean, how does it look like, the problems? Another problem I'm giving you, just think, the annation rate coming to the term of R5 N palladium H2. whole 2 plus by I minus decreases from pH 5 to 9, but increases at higher pH. Explain. So what does okay? So you know from what does it mean by anation? Do you know what is the meaning of the term anation? Yes or no? Do you know what is the meaning of the term anation? No. So the anation means that uh, you'll find it in many places. So the replacement of water by an anion. Okay, now look at the problem. Just looking at the problem, what is coming to your mind? Immediately, what is coming to your mind? What term? Look at the pH factor. Look at the pH factor. So just think of what are the things that you have read, I mean, in the reaction mechanism. What are the special things that you have read? And then you'll immediately remember. Any guess? So water is replaced by I minus, and that in rate increases at very high pH. Okay, whatever you feel, you tell something. Good electron donor. So electron donor means, but take care of the point at high pH. So what I minus is a good electron donor. If it is a good electron donor, in all the cases it is good electron donor. So why the rate increases at high pH? That gives you the one line answer about the mechanism. High pH is the factor. Why at high pH the reaction rate increases? What are the mechanisms that you have read? None of you remember the name. It was a name reaction. I mean, name of the reaction says it all. Anybody just go to the other last day slide, or if you have you are doing it in laptop, and any guess? Look at the question, and then this water is replaced by I minus, and the reaction rate increases at higher pH. That is the point. Okay, I think you are not thinking in this. So this is base hydrolysis. So you just go to the base hydrolysis mechanism, and instead of OH minus, you just put the I minus, right? And then you can see what is the reaction mechanism. So I think that is all, and I shall give you some question for this doing in the during this break, and those who are in West Bengal enjoy puja very well, and thank you for the loss.